So for our tutorial problems, we start with chapter 1, solved problems. And our question 1.1 reads, a continuous time signal x of t is shown as in figure 117. Sketch and label each of the following signals. So we have signal A, x of t minus 1, B, x of 2t, C, x of t over 2, and D, x of negative t. The first thing is to identify that this is our function of t, and the best way to do that is to define your t in terms of mathematical equation. And how I did it is just figured out that the gradient m of this bit is equivalent to the change in y, which is 3, over change in x, which is 4. Therefore, that is the gradient, and therefore our time axis is t, and the y-intercept or x t of it, or yeah, the y-intercept is 0. And therefore, here you have 0. That's your y-intercept. If you remember the typical equation of a linear equation, it normally represents x of t, y is equals to m of x plus c. This is normally the y-intercept, and this is the gradient, and y is the dependent function, the one that now in our case we are referring to as our x of t, and our t in our x-axis is now our time, and therefore we can see that the y-intercept is 0 where the line cuts the y-axis, and therefore we can categorically determine that our gradient is 0 over 4. That is how I've done it here. And then the other most important thing to determine is the scale or the range of our equation, at which point is our equation applicable. And we can see that this line is applicable between t equals to 0 to t equals to 4. So we can say that that is where this equation is valid. Therefore, it is 0 anywhere else. So that is how we can mathematically represent our x of t. And therefore, when you are being asked now to evaluate x of t minus 2, the best thing is now to replace t. What we just observe is that this is a time shifted version of our function. Therefore, the gradient is not going to change, but our y-intercept is going to change. And we just introduce our change, which is negative 2. And for that reason, our range will also change, because it was you are just replacing our t with t minus 2. And when you do that, you can solve this by adding 2 on both sides. You have t, or the lower limit now is 2, and it is t is now going to vary between 2, and when you plus 6 on this side, 2 on this side becomes 6. Therefore, our range is going to vary between 2 and 6, and our limit is going to change. Our gradient is going to remain as it is. The only item that is going to change is the y-intercept. And for that reason, therefore, we can observe how that diagram is drawn. And we can see here, figure 1.7, this 1.8a. Figure 1.8a simply shows that our validity of our equation now varies between 2 to 6. And our limit, our gradient still remains at 3 over 4. And if you are to plot, to extrapolate this line, you would actually see that it would cross the y-axis or the x of t axis at negative 2. And therefore, we have seen that this is our y-intercept. So that is how ideally you would represent equation the shifted version of 1 of a. Okay, the first question that we have been given. And now for the second one, the best thing is to always start with your definition of the equation. Where now we are multiplying with a scalar or coefficient. Therefore, what that coefficient will do is just replace our t with 2 of t. And therefore, what will change now is the gradient. The gradient will now become 3 over 2, and therefore it has increased. And therefore also our range will also vary. When you replace here with 2t, to our original scale, then and divide both sides by 2, you can see that our limit is now varying from 0 to 2 instead of 0 to 4. And therefore, as you can see in figure 18b, you can definitely see that our gradient has now increased. It was 3/4 before, therefore it has become a sharper gradient, now a steeper slope, but our limit has reduced to between 0 and 2. Similarly, you can look at question t of when t over 2 is our function, and again the gradient will change. So you will have that the new gradient will be 3/8. That is less steep or a smaller gradient than we had before, and therefore we also replace our new function of t here to be 2/2, and therefore when you multiply both sides with 2, you get the new range to be 0 to 8. Therefore, as you can see in figure 1118c, you can simply see the same thing, that our gradient varies, has become less steep, and again our range has become bigger from 0 to 8. And lastly, we see that when we have now our function of t becomes negative, we do the same, and we observe that the gradient will change to become negative, and our range, initially we were saying that this is how it varies. Therefore, when you multiply both sides with negative, what it does is that it causes the inequality sign to change. So idea initially it would become 0 is less than, okay, that is not how you say, because it is causing the inequality to change. Therefore, it will be say 0 is greater than t, and t is greater than -4. But this is not a proper or acceptable method of representing this one. So the best thing is now to interchange, and you say that when you bring, just do a simple mathematic. If you look at this and this, you can say that 0 is greater than t. Therefore, you can say 0 is greater than t. So for that reason, you can clearly see that this still means the same. And if you are to consider this one also, you can see that t is greater than -4, and you can still see here. So all I've done is to rearrange, because the best way is to express it in this form, and therefore it actually comes to agree with our definition. And therefore we are saying that our range is now varying between -4 and 0, and our new gradient becomes -0/4. So for that reason, we have our new gradient is now tipping on the negative side, and our range again varies from -4 to 0.